Hi, welcome to KQ12. We're going to be talking about threaded fasteners and static loading. We'll go through chapters 8.4 through 8.7 and also chapter 8.9. So first we're going to talk about how tension joints are really like springs in series. A primary application of bolts and nuts is to clamp parts together so that the applied load puts the bolt in tension. In other words, stretches the bolt out, which in turn applies a clamping force to keep the materials in the bolted region together. So this results in different stiffness sections that act as compression springs in series if we're thinking about the material, which combine according to the regular equation that you've seen before to combine springs in series. So the Shigley notation is shown in the orange box. K1, K2, K3, up to Ki would be the spring rates of each of the clamped materials, and Km is the total spring rate of the clamped materials. Another feature that makes our spring model a bit more complicated is the fact that a long bolt will have threads over just a portion of its length, and hence will have different cross-section areas. So in this picture here, there's a large region or a long region of the bolt that's unthreaded, and then a shorter region of the bolt that is threaded. We don't need threads extending over the whole fastener because we only need threads essentially where the bolt is going to engage with the nut to hold the materials together. So having part of the bolt that's threaded and part of the bolt that's unthreaded also results in different stiffness sections that act as tension springs in series. So the purple box shows the spring rate of the threaded portion within the clamped zone. So the clamped zone is shown with little l. I know it's hard to see, but you can look at your textbook. So purple box, again, shows the spring rate of the threaded portion. KT is the spring rate. AT is the tensile stress area of the bolt, which you'll look up in a table. E is the modulus of elasticity, and LT is the length of the threaded region of the clamped zone. The green box shows the spring rate of the unthreaded portion within the clamped zone. KD is the spring rate, AD is the total cross-sectional area, E again is the modulus of elasticity, and LD is the length of the unthreaded region of the bolt, again within the clamped zone. We have LD and LT. So the spring rates of the threaded and unthreaded portions can be combined into an estimated effective stiffness within the clamped zone. And this is given as KB. So the red box is showing KB, and that's what we just would call the fastener stiffness. So we need to determine the stiffness of the fastener, but also the stiffness of the members or materials within the clamped zone. Both of these stiffnesses must be known in order to learn what happens when the assembled connection is subjected to external tensile loading. And the stiffness of the members is actually pretty difficult to obtain because the compression region spreads out between the bolt head and the nut, and hence the area is not uniform. That's what this picture on the right is showing here. Some ultrasonic techniques have been used to determine this pressure distribution shown here in pink. Results show that the pressure stays high out to about 1.5 bolt radii. So the Shigley approach to modeling or representing the compression area of the materials is with what's called the frustum of a hollow cone. And you'll see that this is important because we need this frustum geometry to figure out the stiffness of the members in series. So picture A just shows a bolted joint, two materials, presumably different materials. And then again, this frustum shape shows the pressure distribution within the clamped region. So note that there are three frustums in B, sort of this medium pink, this dark pink, and this light pink. The total height that the frustum spans here is 0.6725 inches plus 0.6725 inches. So it's a symmetrical shape, but we don't have equal thicknesses of materials. So this top material here is a 1/2 inch, and the bottom material here is 3/4 inch. So some of what we might call the top frustum extends into the second piece of material, resulting in 3 different frustums. All right, so back to what I was saying. Calculating the spring rate of the materials is a bit of a process. It requires a frustum analysis. The main equation is shown in the green box here, and it's equation 820. It has 4 different inputs: the material's modulus of elasticity, the fastener major diameter, the diameter of the top frustum, which is the big D, and the frustum thickness, which is little t, also just think of it as like the height of the frustum. And then again, little d is the major diameter of the fastener. So equation 820 has to be solved separately for each frustum in the joint. So if we go back to our previous picture, we got to solve this equation 820 for three times, which is why our analysis tool is super helpful. So let's just dive into an example. This is a modification of example 8.2. To set your expectations accordingly, this example took me about 2.5 hours to get through the first time in order to really understand what was happening and to program my analysis tool and make sure it was calibrated correctly. So don't rush this process. You have a couple days for this knowledge quest, and I'm expecting that this is going to take you a little bit of time. Figuring out the frustum geometry, like I said, is probably the most time-consuming, but please make sure you understand how to do it so the final exam doesn't catch you off guard. It's all about just going slowly and using lots of triangle geometry. So here we go. Two plates are clamped by washer-faced 1/2 inch 20 UNF by 1.5 inches SAE grade 5 bolts. It's kind of a mouthful. Each with the standard 1/2 N steel plain washer. So here's our washer sitting right underneath the head of the bolt. And in this example, we're just going to determine the spring rates of the material and the spring rates of the bolt. So determine the member spring rate Km if the top plate is steel and the bottom plate is gray cast iron, and determine the bolt spring rate Kb. So here we go. I will step through this problem and also show you my analysis tool. So I just have the problem statement repeated here, as well as equation 820 for reference. So we are going to find the K value for 3 different frusta, 1, 2, and 3. So some preliminary things before we get started. You'll see that the geometry has been provided for you in this first example, but that won't always be the case. But this is a nice first example to step through because you don't have to worry about getting the wrong geometry, and you can use this example to calibrate your tool pretty well. So one kind of rule of thumb I want to point out is this relationship here. So the top of the frustum, the first frustum, is given as 0.75, and that comes from this rule of thumb of the top of the frustum being 1.5 times the diameter. So the diameter D is given as 1/2 inch. So that's the major diameter of the bolt. So that's where we get this 0.75. So K1, just following the green box here, 0.5774 times pi. E is 30 e to the 6th psi, so that's the modulus of elasticity of steel. And then again, the major diameter is 0.5, so that's all here in the numerator. And then the denominator is a function of the thickness, the diameter of the top frustum, and then again the fastener diameter. So those are the 3 dimensions you need to find. So in this example, since the washer and top plate are both steel with the same modulus of elasticity, they can be considered a single frustum. So our first frustum actually extends like this. So it includes the washer. So we have to include the washer height in our calculation of the height of the frustum. A better term for washer height is washer thickness, which is what it actually is. And for this, you need table A32, and you're going to look for the thickness of a standard 1/2 N steel plain washer. So let me show you my tool. So table A32, basic dimensions of American Standard plain washers, all dimensions in inches. We go to 1/2 N, and it gives the washer size, inner diameter, outer diameter, and then the thickness of 0.095 inches. So table A32 should be in your analysis tool. But again, in this case, the dimensions are given. So our T in this case is 0.6725 minus the thickness of the dark pink frustum, so minus 0.0755. So that's what I have here, T1, 0.6725 minus 0.0775. So T equals 0.595 inches. So we have 2 out of the 3 things that we need. We have D, we have T, And then the diameter, that's easy so long as the frustums are at the top or the bottom of the joint, because we're just going to use this relationship. Big D equals 1.5 times the major diameter of the fastener. So this is my output from the analysis tool. K is 30.8 megapound force per inch. So this would be for the upper steel frustum. Just to show you how that's positioned in my analysis tool. So same thing here, I just started out on the left, finding member material stiffness, and then I have equation 820 repeated 3 times. So this dark pink region, we can think of this as the upper cast iron frustum, because we are in the cast iron region here, but we're just focusing on this dark pink frustum. So we're figuring out that K2. So little d is going to stay the same. Big D is given in the figure as 1.437 inches, but make sure you understand how this was found. So I had to look at it for a minute. And we know this 0.75, so we know basically this length here, but we need to figure out this little x and this little x. So for that, you can just use law of tangents. So alpha is given in Shigley as 30 degrees, and that's essentially the cone angle, and that's going to be constant for all of the bolted joint problems that we consider. So tangent of 30 degrees equals x over the thickness that we've already found from K1, 0.595. So if we do 0.75, so that's this distance here plus 2 times x. So here and here, we get our D of 1.437. So the middle frustum is going to probably take the most amount of time, but it's going to be the same process. And then the thickness of this frustum is 0.0775 inches. So that is equal to 0.6725 minus the washer thickness, 0.095, minus the thickness of the steel plate, 1/2 inch. So my analysis tool had to look up the modulus of elasticity for cast iron, 14.5 MPSI, major diameter 0.5, big D 1.437, thickness 0.0775. You saw where these numbers came from, and that yields a K2 that is quite a bit larger than K1, so 285.5 megapounds per inch. The bottom cast iron frustum is pretty easy. So again, little d is going to be the fastener diameter, the thickness 0.6725, and then the big D we already found from the top frustum, so 0.75. So again, that's in my analysis tool in this third input area for equation 820, get K3 of 14.15 megapounds per inch. Then the total spring rate of the members is 1 divided by 1 over K1 plus 1 over K2 plus 1 over K3. So next we're going to find the bolt spring rate, KB.
Here is our formula for the bolt spring rate, KB. It's equal to AD, AT. Here's our formula for the bolt spring rate, KB. We're going to go through each of these terms and how you obtain them. So AD is, again, the area of the unthreaded portion, and that's equal to pi over 4 times the fastener diameter squared. So in our case, the fastener diameter is 1/2 inch. AT is the area of the threaded portion, and to look up AT, you can reference table 8.1 or 8.2, and I'll show you those in a second. And then also table 8.5 is really handy to put in your analysis tool. It is physical constants of materials, and from this table you can find the modulus of elasticity. So I'm going to show you my analysis tool, and then we'll come back to the rest of these terms. We just talked about AD, AT, and E. So D is a 1/2 inch. AD would be an automatic calculation, so it's orange. AT, reference table 8.2. So table 8.2, our size designation is 1/2. And if you remember, we have a fine series bolt, so our tensile stress area AT is 0.1599 inches squared. So that's an input here, 0.1599. E, modulus of elasticity, is 30 MPSI. And again, the table for that is 8.5. Carbon steel, modulus of elasticity E, 30 MPSI. Okay, so that takes care of the numerator and some of the denominator. The LT and the LD are kind of a pain. So the LT is the length of the threaded portion in the grip. So circled in orange here is our LT, length of the threaded portion in the grip. So LT is calculated by little l minus little ld, where little l is the thickness of all material squeezed between the face of bolt and nut. So here's little l, it's all the material squeezed in between the face of the bolt and the nut. And then LD is the length of the unthreaded portion in the grip. So this distance here, LD. So it's the unthreaded portion within the grip. So to find LD and LT, start with LD. LD is equal to the fastener length L minus LT, which is the entire threaded length of the fastener. And so for this, you just reference table 8.7. So there's a subtlety here. So big LT, again, is the threaded length of the entire fastener. So here, so some of the threaded portion is extending past the clamped zone, where little LT is the threaded portion within the clamped region. So let's look at table 8.7. Threaded length LT for inch series fasteners, we have LT equals, and we have two different ranges. For a fastener length less than or equal to 6 inches, which is what we're given, it's 2 times the fastener diameter plus 1/4 inch. So 1.25 inches. We also need the fastener length L, which was given in the problem statement. So right here, 2 plates are clamped by washer face 1/2 inch 20 UNF by 1.5 inch SAE grade 5 bolts. So the length, the big L, is 1.5 or 1.5. So in general, L being the fastener length is in table 8.7. L has to be greater than or equal to little l plus h, where again, little l is the thickness of all material squeezed between face of bolt and face of nut. And h is the height of the nut, which you can find from table 831 if you have to. In this case, we were just given L in the problem statement, so 1.5 inches. So we have L and we have LT, so we can find LD. 1.5 minus 1.25 gives us LD of 0.25 inches. And then lastly, we can find LT, the length, little LT, the length of the threaded portion in the grip. So it's little l minus little LD. So 1.345 inches minus 0.25 inches gives us LT, little LT, 1.095 inches. All right, so that's a little painful, figuring out all the L's and the little L's and the D's and the T's. But we finally get to our bolt stiffness of 3.694 megapounds per inch. So really do take your time trying to go through and understand that example and use it to calibrate your analysis tool before moving on. So next we're going to talk about bolt strength. Strength is specified by stating SAE or ASTM minimum quantities. So the minimum proof load is the max load a bolt can withstand without permanent set. Minimum proof load is the proof load divided by the tensile stress area. So that's just the form of sigma equals P over A, and the minimum tensile strength. So you'll be referencing tables 8.9, 8.10, and 8.11. Table 8.9 shows SAE specifications for steel bolts. Bolt grades are numbered according to the tensile strength. So here down this column is the bolt grade. And then also the grade of the nut should match the grade of the bolt. All specification grade bolts in the United States have a manufacturer's mark or logo in addition to the grade marking on the head. And these marks confirm that the bolt meets or exceeds specifications. If the marks are missing, you might have an imported bolt. And for imported bolts in the US, there are no requirements to meet specifications. So check for these head markings. ASTM specifications for steel bolts are presented in Table 8.10. So again, these 3 minimum values, proof strength, tensile strength, and yield strength. Specifications for metric fasteners are given in Table 8.11. So just different nomenclature, but still these 3 minimum values are being reported. And we'll be referring to these bolt strength values soon. I'm just showing you where they come from. Okay, so now we'll talk about what happens when an external tensile load P is applied to a bolted connection. So when this load P is applied, it is split into two different components, PM and PB. PM is a portion of the load taken by the material, and PB is a portion of the load taken by the bolt. We will come back to this, but first we're going to talk a little bit about preloading. So before a joint is loaded, however, it's important to preload the joint by tightening the bolts with enough torque to create tensile loads that approach the bolt's proof strength. So why do we do preloading? High preloads make it very unlikely that the bolts will break in service if they don't break while being tensioned or tightened. The reasons for this are kind of subtle and require an understanding of how the elasticities of the bolt and the clamped members interact when the bolt is tightened and when the external load is later applied. I think it's interesting, and I'm going to try to explain with this figure down here. So figure A shows a bolt clamping a spring, which is analogous of clamped material, like steel plates. Whatever material is clamped will have a spring constant and will compress when the bolt is tightened. The bolt, also being elastic, will stretch out when tightened. So in B, let's say that we grabbed the nut and we pulled it down with 100 pounds and we stuck a piece of scrap metal between the nut and the ground plane to serve as a stop. This is what B is showing. So the bolt is tensioned here. It's being pulled out and it now has 100 pounds of tensile preload in it, and the spring has 100 pounds of compressive preload. So we want that squeezing of the material together. Okay, so now in C, we can remove the 100 pounds, and since this stop is here, this preload remains in the assembly even after that 100-pound weight is removed because of the scrap of steel that we stuck in there. This situation is identical to that which would result if the nut had been tightened with a wrench to compress the spring, aka the material, the same amount. Figure D shows a new load of 90 pounds applied to the bolt. So again, the bolt has been preloaded, and now we're applying this new load of 90 pounds. The tension in the bolt is still 100 pounds and will be so regardless of the external load applied until that load exceeds the preload of 100 pounds. So figure E shows what happens when the load exceeds the preload. The larger load, the 110-pound load, further compresses the spring and the steel scrap falls out, breaking the contact between the nut and the ground plane, and the bolt tension is now equal to the new applied load of 110 pounds. So in this case, the bolt and the material separate, and the bolt takes the full amount of the applied load. So that's probably more information than you need about preloading, but I think it's kind of interesting. So let's go back to where we were talking about how the applied load is split into two components, the material and the bolt portion. Just kind of stay with me here while I explain a little bit of stuff. We can rearrange Hooke's law to write an expression for elongation equaling the portion of the load taken up by the clamped materials over the spring constant Km. And elongation also equals the portion of the load taken up by the bolt divided by the bolt spring constant Km. So we can equate these two expressions for elongation. So in other words, set them equal to each other. To get this expression, PM equals PB times Km divided by KB. And then we also remember our original formula. The total load P is equal to PM plus PB. So we get this new expression for PB equaling KB, the bolt spring constant, times P over KB plus Km, which we are going to set equal to C times P. And this C is what becomes useful. So C is called the stiffness constant of the joint, and it is equal to the spring constant of the bolt divided by the sum of the bolt and member spring constants. So this pink box is really the useful part of this discussion. So bringing us to our final destination, the resultant bolt load FB is C pleat plus the preload that we just talked about, and the resultant load on the connected members FM is the product of 1 minus C times the total load minus the preload. And these expressions are only valid as long as some clamping load remains in the members. So figure 812 compares the stiffnesses of steel bolts to steel members. So one of the key things to notice is how much more of the external load is taken by the members. So it's over 80% in all of the cases, as compared to how much of the external load is taken by the fastener itself. So this C value is kind of useful in showing us that percentage of basically where the load goes. Another interesting thing to note is how making the grip longer, so 2 inches compared to 3 compared to 4 inches, causes the members to take on an even greater percentage of the external load. So that brings us to our concept check, joint factor of safety. This is what you'll be doing for the quiz. It's going to tie everything together, and I think is going to take you a minute. A 2-inch steel plate and a 1-inch cast iron plate are compressed with 1 bolt and nut. The bolt is 1/2 inch, 13 UNC, regular hexagonal. So A, you're going to determine a suitable length for the bolt, round it up to the nearest 1/4 inch. Round it up meaning make it a little bit longer. So use table A31 to determine the nut height. Then include the nut height and the material thickness to determine the exact length, and then round up. And that's because we want a couple threads protruding from the nut in a bolted joint. I think we talked about that earlier. Then B, determine the bolt stiffness. So use E equals 30, MPSI for steel. Again, table A5, physical constants of materials should be in your tool. It's pretty useful. Use table 8.7 like we talked about to find LT. No washer is mentioned, so the length of the clamped zone is just the thickness of the materials. And then use table 8.2 like you saw before to find the tensile stress area. And then determining the stiffness of the members, there is an image of the frustum on the next slide. And then once you have these two stiffnesses, you can determine the stiffness constant of the joint. So this picture should be useful. Big D in your frustum calculation, the top of the frustum comes from the rule of thumb, 1.5 times the fastener diameter. The fastener diameter is given here, 1/2 inch. So that part's at least done for you. L equals 3 inches, the length of the clamped zone. Because no washer is mentioned, the length of the clamped zone is just the thickness of the materials. And then for each of these 3 frusta, you need to find the big D, which I guess was given for the top and the bottom, little d, which are given, and then the height or the thickness of each frustum. So that's it for this knowledge quest. I know it's kind of a lot of material for this KQ, but that's why you have 2 days to do it, and just reach out with questions. Thanks for watching.